Welcome to this explainer. I am super excited you're here today because we're going to unpack a massive, largely invisible world that literally keeps our modern lives running. We're talking about a world of colossal steel leviathans, meticulously planned global networks, and perfectly standardized metal boxes. Basically, it's the circulatory system of the entire global economy, the international liner shipping industry.
Seriously, think about it for a second. Look around you right now. The clothes you're wearing, the phone or computer you're using, the furniture in your home, maybe even the coffee in your mug. How did all of this stuff, sourced from literal opposite corners of the globe, actually reach your local shelves and ultimately your hands? It's something most of us just completely take for granted. We just click order and boom, expect it to magically appear. But the reality behind that magic trick is an astonishingly complex physical internet.
And to give you a sense of just how massive this hidden world really is, liner vessels carry roughly 60% of all goods, by value, moved internationally by sea every single year. So we're talking about hundreds of billions of dollars contributing to the global GDP annually. Without this hidden lifeline, global trade as we know it, it would absolutely just cease to exist.
Okay, let's dive into this. Here's our roadmap for today. First, the global trade lifeline. Second, navigating the ocean routes. Third, the evolution of container ships. Fourth, understanding ship capacity. And finally, inside the shipping container.
Starting with Section 1, the global trade lifeline, the circulatory system of the economy.
So the absolutely crucial starting point is understanding exactly what we mean when we say liner shipping. You see, it's not just any boat on the water. Liner shipping is the service of transporting goods using high-capacity ocean-going ships that transit regular routes on very strict, fixed schedules. This is totally unlike what the industry calls tramp ships, which basically wander the globe, picking up random cargo where they happen to find it. Liner services are highly predictable. In fact, there are over 2,000 of these specific liner services in operation today. They mostly provide fixed weekly departures, so it's a lot like a public bus or a train schedule, but on a planetary scale.
And the efficiency here? It's just staggering. Over the course of a year, a single large container ship might carry over 200,000 container loads of cargo. On just one voyage, some of these giant ships can transport upward of 18,000 containers. To move that exact same amount of cargo over land or through the air, you would need hundreds of massive freight planes, miles upon miles of rail cars, and massive fleets of trucks. By utilizing the ocean, this industry keeps costs incredibly low for you and me as consumers. It's hands down the most efficient mode of transport for bulk goods.
Moving right along to Section 2, navigating the ocean routes, the highways of the sea.
So let's talk about the end-to-end service route. This is the traditional way of doing things. A ship sails from a starting point, calls on various loading ports, crosses an ocean to a range of discharging ports, and then it simply turns around and comes right back over that exact same route. For example, think about the India to Europe trade lane. A ship hits ports in India and the Middle East, travels straight up through the Red Sea and the Suez Canal, drops its cargo off across northern Europe, and then heads back. It's pretty straightforward, point A to point B and back again.
But things get quite a bit more complex when you look at a pendulum service route. Notice how this path is totally different. Instead of just bouncing between two regions, a pendulum links two or more main trade routes together. In its most ambitious form, a pendulum service might start at the U.S. East Coast, cross the Atlantic or travel all the way via the Cape, swing through Asia, and then continue right onto the U.S. West Coast. Now, why go through all that trouble? Because it allows shipping lines to bypass the physical width limitations of the Panama Canal, and that means they can use significantly larger ships to link the globe.
Which perfectly sets up Section 3, the evolution of container ships, engineering leviathans.
Containerization actually kicked off in the mid-1950s with ships like the Ideal X, which, crazy enough, was really just a converted World War II T-2 tanker. That thing maxed out at around 1,000 containers. Back then, they literally had to carry their own onboard cranes to load and unload. But as the ports upgraded, the ships rapidly evolved. By 1968, we got the first fully cellular ships. That meant the entire ship was designed as a grid to perfectly slot containers above and below deck, no onboard cranes needed anymore. Fast forward to 1985, and they hit the absolute maximum size that could physically squeeze through the old Panama Canal, carrying about 4,000 containers. But global demand for goods didn't stop growing, and well, neither did the engineers. We saw this massive leap to very large container ships in 2006, and by 2013, we officially entered the era of the ultra-large container ships, which carry upwards of 18,000 boxes at a time.
And this evolution is just wild to look at. We went from carrying containers just a few rows wide on the deck all the way to these absolute monsters of the sea, the ultra-large container ships. I mean, these ships are getting so incredibly massive that they're approaching the technical limits of even the Suez Canal. The driving force behind all this is economies of scale. Basically, the more containers you can pack onto a single voyage, the lower the cost per container. But on the flip side, it puts massive pressure on global ports. They constantly have to dredge deeper channels and build these gigantic new cranes just to handle these giants.
All right, Section 4, Understanding Ship Capacity, Theory versus Reality.
Now, you will often hear a ship marketed by its nominal capacity, and that is really just the geometric theoretical limit. It's the maximum number of containers a ship could carry if every single box was perfectly empty and perfectly uniform. But out on the actual water, gravity is the boss. Effective capacity is the real-world carrying capability of laden or loaded boxes. If a specific trade route naturally deals with very heavy cargo, the ship is going to hit its weight limit or its draft limit way before it runs out of physical geometric space on deck. So a ship advertised to hold 2,500 empty boxes might realistically only be able to safely carry 2,000 fully loaded ones. It is an absolutely crucial distinction in the shipping business.
And finally, Section 5, Inside the Shipping Container. The building blocks of trade.
Now, you might be thinking a shipping container is just a simple metal box, right? Actually, the intermodal ISO container is a highly specialized piece of equipment. It is engineered to withstand extreme marine environments, unbelievable stacking weight, and constant handling by massive cranes. And there isn't just one type. To accommodate our incredibly diverse global economy, shipping lines have developed a whole entire family of customized boxes.
Let's break a few of these down really quickly. You've got your standard general-purpose boxes for everyday dry goods. Some of these are even specially fitted with hanging bars inside, so high-fashion garments arrive completely wrinkle-free and runway-ready directly to the store. Then you have flat racks. These have no sidewalls or roof, which makes them perfect for heavy, over-dimensional cargo. Think huge tractors or factory machinery. Then there are reefers, which are basically fully integrated refrigerators, keeping perishable food anywhere from a freezing -25°C to a warm +25°C. And you even have highly specialized tank containers designed explicitly to carry bulk liquid cargo safely across the ocean.
But whether we're talking about a 20-foot box or a 40-foot box, the hardcore structural specifications are really what make the whole system work. Look at the maximum gross weight. A single standard 20-foot container can handle over 30,000 kilograms. That is more than 66,000 pounds of weight. The sheer engineering required to ensure that a box doesn't crumple like a soda can when it's stacked 8 or 10 high deep in the belly of a pitching ship in a rough sea, it's just phenomenal.
And because of those extreme physical forces out at sea, there are strict laws of physics you have to follow when stuffing or loading a container. It's literally the most high-stakes game of Tetris in the world. The guidelines are absolute. You must spread the weight evenly. You have to keep the center of gravity as low and as central as humanly possible. Because a high center of gravity inside a single box, that translates to a very dangerous imbalance for the entire ship once it's out on the ocean. And finally, everything has to be perfectly secured with wedges and lashings so absolutely nothing can shift or collapse during transport.
All of this leaves us with a pretty critical thought to ponder. We've just explored this vast, highly optimized, incredibly efficient intermodal network of massive ships and standardized boxes. But here's the catch. This network operates on incredibly tight fixed schedules with very, very little margin for error. If a single disruption, say a blocked canal, a port strike, or even a localized weather event, happens anywhere in this interconnected system, it cascades. It delays millions of products worldwide. It really forces us to ask, just how resilient is this invisible lifeline of our modern world? It's definitely something worth thinking about the next time you casually click order. Thank you so much for joining me for this explainer. Keep asking questions, and I'll catch you next time.